introduce our next speaker. So our next speaker is Achal Bassamboo, who's the Charles E. Morrison Professor of Operations Management at Kellogg, where he's been a faculty since 2005. Achal broadly works in service operations, including revenue management, information design. He was awarded the Young Scholar Award by the M.SOM Society. What I can say about Achal is that he's a wonderful colleague and a wonderful teacher. The first time I think I saw Achal was in 2009. You giving a talk at Cornell, and what sort of struck me was, first of all, like how good a presentation you gave, and also how you could identify very interesting, unexplored research questions. So I'm really looking forward to Achal's talk today. So thanks.
Thank you so much, Varun. So first of all, thank you so much for the organizers. I know Sandeep had to go, but it's real pleasure to be here and learning the new topics and the new areas. So thank you so much for everyone who's participating. Uh, I'm going to talk about the asymptotically optimal adaptive A/B testing for average treatment effect. And this is joint work with Vikas and Sandeep. So that's why this got a shoe in. In terms of what I would like you to think about in terms of connecting it, I would say this builds on the work that we saw in the tutorial about confidence building, right? The confidence interval construction that was discussed on day one and day two. It will be different from that, but it will be in that same spirit about that's what I want to do. So all of us know about A/B testing, right? Means, in fact, I would argue that every time you open up an app, you are either A or in B category, more or less. So the question that we have is, I'm going to just start with the context so that we all understand what it is and what we're going to focus on. And then I'll get into the key result and trying to understand how do we construct that and what is different compared to the literature. So A/B testing is this method. By the way, show of hands, how many of you know what A/B testing is? Perfect. So A/B testing is basically a method of comparing two versions. So think about Uber wants to have a different layout of the app. It wants to know whether this will be received better or not. In fundraising, Obama gets a lot of credit for using it for the very first time to see what appeals to the people who come and donate for his campaign. So the pictures that he was showing, whether they should have just Obama, Obama has in family, the hope written on it, and they did A/B testing, and it's deemed that that actually worked and created a lot of money that he was able to generate. Okay? So what A/B testing usually comes with is there are two versions, and the idea is I'm going to show this to the audience or the customers, and I will measure a metric of interest. For the purpose of the talk, it will be agnostic of what exactly that metric is, but we will have perfect measurement of that particular, but the response is random in the sense that we will have a noisy outcome. That's what we're not able to see. This is used very widely, and this is a good way of making data-driven decisions. So rather than saying that it's my hunch that this looks better, we can actually ask the end consumer. There is nothing better than that. That's what this allows us to do. Now let's look at an example of this. So imagine this is Netflix. Netflix can actually have two types of layout. It wants to keep you as long as possible on the platform. This is how they can actually try to keep you as engaged and giving you value. So they might have two treatments. One could be one of the videos could be blown up. The other one is there are lots of small videos to show you a lot of variety. It's not clear upfront which version is better. So we throw it at the customers, and we will get the click-through rate, which is how many people are clicking on such web pages and continuing on. And based off that, we will say one is better than the other. Now, one of the things that people have used these are called randomized controlled trial, very simple version of it. Go ahead. Very good. So that's exactly what I'm going to say next. So imagine the visitors that are coming to the app or to the website. I divvy them up 50-50. Half of them get version A, half of them get version B. And we will measure which variation is doing better. And at the end of the experiment, I will go with whatever the click-through rate or whatever metric I'm interested in, I'll go through. I'm showing this for the electronics, for the web pages or electronic information. This has been used very widely in medicine. So think about people were giving, we are thinking about a medicine. So we'll take the people and give them medicine A and to check its efficacy, because to show that it actually works, the other group might even be given a placebo, right? So it's essentially just trying to see like how many people feel that they got better just because they were part of the group. And if I can see that it's actually cured, then I will conclude that yes, that is better and I want to go. Now, this is something that has been widely studied, and there is more sophistication that has happened over the past, I would say, decade, where people have used banded types of control to come up with the conclusion. This is statistics problem, as you can think about it. And absolutely the same way, if you remember, when we were doing the confidence interval building, there was a question about whether we are to the left or the right of 0.5. This is very similar to that question. Now, in the setup of a website design, there is a more informative and more nuanced question. And that question is that I don't want to just choose the better version, but I also want to know by how much it is better. This could be because of variety of reasons. Because you're going to choose a particular version, it could be plausible that you will have to invest for it, right? So if I take that investment, divvy up on the per impression basis, I want to know that, okay, if the cost is more versus, remember, we are never just thinking about profit, we are always thinking about, we should always think about profit, not just revenue. So we want to think about also the cost, which means that we want to look at the delta rather than just knowing A is better than. So that's what the goal is. We will be looking at a more informative objective. We want to know the average treatment effect. And in this particular case, let's suppose the version A has a conversion of 21% and version B has a conversion of 38%. Your average treatment effect will be the difference between the two, which will be 38% minus 21%. All okay? So, now, as we know from statistics, we will never, ever, ever going to know the parameter for sure, right? This is something that the statistics teaches us, that you can only get a confidence interval. You never know this truly 21%, 38%. That could be underlying, but you will only have noisy estimates. So I'm just going to be very clear about it. I am not interested in estimating 21% or 38%. My goal is to figure out a confidence interval for this difference, and I will refer to it as ATE, which is the average treatment effect. So with that, we are actually well posed to at least put the agenda on the screen. So here are the three research questions that we will try to address. Number one, what is the best way to allocate arriving customers to treatment A versus treatment B? And the objective is the ATE construction. Second question, how do we construct the ATE estimator? As we saw, there were very interesting ideas about using normality, but then it goes beyond. We want not just an asymptotic result, we want a finite end result, and we want finite guarantee. So without knowing the distributions themselves, how exactly would you construct those confidence intervals? And the third question, based on if we get to it, is does the ATE and BTI lead to the same allocation? So as you can see that I'm going to do this dynamically. I'm going to give the impression of A versus B to the customers. And the question is, if I tell you that my goal is average treatment effect estimation versus BTI, which stands for best treatment identification, will I be using the same allocation rule or a different allocation? Because if it's a different allocation rule, it is basically saying you have to tell me upfront what you want to do. And I'm going to just spill the beans at this point. The answer is no, it's not always the same allocation rule. It actually really matters what you want to do. Okay? The next thing is, even before I can say this, I haven't described what the objective function is, right? If I say, what is the best way to allocate, you have to clearly tell me what you want to do. So it is right now, I'm just saying best, but I have to define what that best means. So that's what I will start. So what's the objective here? And here comes an interesting thing. If I look at the ATE problem, which is the average treatment effect problem, it has three metrics that goes into it. Number one, the accuracy of the conclusion. Second, the length of the experiment. and third, the width of the estimate. So let's go over each one of them to make sure that we are on the same page. Width of the estimator, we are all comfortable with, right? You will give me an answer, the ATE, you will tell me plus minus something, and I want the width to be as narrow as possible. Length of the experiment is also very clear. How many impressions did you show until you reach the conclusion? The accuracy of the conclusion is how confident you are about the conclusion. So this is when we talk about like 95% confidence, that's what is going into the accuracy of our conclusion. Now, just to contrast between this problem, which is well studied, which is BTI and ATE, notice the following. ATE has all the three. BTI does not have the width. So BTI typically only has these two, which is the accuracy of the conclusion and the length of experiment. And in the literature, both versions have been studied. What do I mean by both versions? Where one is trying to constrain the accuracy of the conclusion and trying to minimize the length of the experiment. And in the similar spirit, given a length, trying to get the maximum accuracy. You can see both of them have been studied, and people have shown that there are different conclusions that you get out of it, which is one is called the delta pack kind of policies, and the other one is fixed confidence kind of thing. Now, given that ATE has three, that means this is a much richer problem, and it has its own slew of questions that needs to be addressed. And this became a big part of the class's dissertation, right? So the problem that I will be presenting today is looking at specifically one of it, which is we want to minimize the length of the experiment. And I would let you guys look at what Vikas is going to write in the couple of years, which addresses the remaining problems. Okay? So here is our setting. What is the setup? We want to minimize the expected length of the experiment with the constraint that the probability, the true ATE, the actual average treatment effect lies in the interval that you're giving me is at least delta. So whenever I say this statement, I just want to be very careful about it. When we write this, many times we feel like the true ATE lies in the confidence interval. Just to be clear about it, the way you should say that statement is the confidence interval that you're giving me covers the true ATE, because true ATE is actually a constant. It is the confidence interval that I'm going to give you will be the random quantity here. Just want to emphasize this because that's the important way to think about the line. Okay. The second thing is, as I mentioned, we have the width of the confidence interval. Because if I don't put another constraint, if I just have the first two, you can always stop at step one and give me a conclusion minus infinity to infinity, right? That's a trivial solution. So that's why you need to have a width of the confidence interval as well, which is we are putting a constraint on it that it is at most epsilon. We are all comfortable with that. I'll take a detour just for a minute, and then I will make all of this mathematical so that we are comfortable with what the setup. Okay. So for ease of notation, so that I don't have to call upon it again and again, I would refer to the confidence interval which satisfy those two constraints. What are those constraints? The probability that the true ATE lies in the confidence interval I'm reporting is at least delta. Sorry, it should be 1 minus delta, my bad on that, because delta is typically small, right? It should be 1 minus delta. You guys are very patient with me. Thank you. Right? And the width of CI is at most epsilon. I will call those as an epsilon delta confidence interval so that I don't have to keep on repeating this very verbose condition. Everyone comfortable with it? Okay. So what will be our approach? Our approach will be, if I look at the exact analysis, it will be analytically intractable because it's a dynamic, you're learning over time. So it's a learning plus statistics put together. So what we will do is we will actually look at an asymptotic regime where delta is going to 0. But the guarantee that I talked about will still be applicable on the way. So it is not like that my guarantee also is only asymptotic. My guarantee still that coverage epsilon delta is still valid at finite n. This was very much also the feature which was presented when we were talking about confidence interval in the tutorial on day 1 and day 2. So I just want to highlight that. Okay. What is the machinery that we will be using? So there is delta correct framework machinery, which is used in bandits. And that machinery essentially points to the fact that you are trying to figure out the better arm. And there are very nice, I would say, very sophisticated information inequalities that they use to construct a lower bound. And you use that lower bound itself to construct the algorithm and prove that it all works. And my goal in this talk is exactly to take you through that journey where you will be thinking about, okay, how exactly is a lower bound constructed? And second, what will be that algorithm? And it will all fall out exactly if we could collectively figure out what the lower bound. So before I do that, here's a question. So it should be 1 minus delta. So that was my bad. So the typo is 1 minus delta. So I'm looking for the probability. You want that probability of confidence to be as close to 1 as possible. Otherwise, this will be like pretty bad. There is a long list of literature on these kind of problems, the things that I'm using. Adaptive experimental design is the first one. Causal inference. ATE is something that economists like to use to measure things. So that comes from there. Sequential testing and pure exploration in multi-arm bandit. This is giving you the hint about the source of machinery where I'll be borrowing from, and these are the papers which are looking at sequential testing, because the approach will be on doing this in an online. So now is the time to put the mathematical framework on it to make it precise so that we are talking in precise terms. And here we go. There is treatment A, which has an outcome which comes from a distribution mu A, and its mean is mu A. There is treatment B, the outcome of that is mu B, and it has a mean mu of B. Okay? Based on that, my average treatment effect, without loss of generality, I can treat anyone A and anything B will be mu A minus mu B. That's what I'm after. And as I mentioned, we will not know it, so we will be constructing a confidence interval around it, and that's what the outcome is. To give a little bit more structure to us, and this structure will be something that we relax in the paper. And the structure is that I'm assuming that mu A and mu B are from exponential family. Just to be clear, if you are learning probability recently, exponential distribution and exponential families are two different words. What is exponential family? Exponential family is you take a particular distribution, and from that, you parameterize, you construct a bunch of families where this theta allows you to have a whole family, which is at the crux of it is there is only one distribution. The beauty of this is this actually captures a lot of distribution that we work with. So for instance, exponential family is definitely part of it. Normal distribution is part of it. And this is single parameter, and there is some nuances with it. And there is a whole Wikipedia about how flexible this system is. Okay? Now, let's talk about the policy that we will have. So notice the policy will need to do three essential things. Number one, it will have to tell me at every step of the way, how do I allocate between treatment A and treatment B? Number two, it will have to tell me when should I stop my experimentation, that I have enough confidence in what I constructed that first its width is less than epsilon, and I'm confident that the probability that the confidence interval covers the true ATE is more than 1 minus delta. Third, it has to have a method by which we will construct that confidence interval. As long as I have these three things, I have the policy, I'm all set. Writing the whole thing mathematically, I have an optimization problem that I had from past. This is how we can write it. We want to minimize the expected length of the experiment. So remember, tau is the stopping time. So we want to minimize the expected tau delta, subject to the probability that the actual true delta, which is the ATE, lies in this random delta L and delta R has to be greater than 1 minus delta. I don't have the typo on this one, guys. Just making sure. And delta R minus delta L has to be less than epsilon. Okay? So this is the epsilon width. So this is the width constraint, the accuracy constraint, and you're minimizing the length of the experiment. All good? Now, what we want to start off with is let's do a very simple policy. And that policy is as follows. We will do randomized controlled trials. And as I mentioned, the randomized controlled trials is a 50-50 split. And we do symmetrical confidence interval, which means that we are going to do an interval which will be going on either side of our estimator. And that width on either side is identical. So if you think about when you learn statistics, we typically go right the midpoint and do plus minus the same amount. So I'm already fixing this. There is no reason for this to be optimal. Everyone comfortable with that? That's one. Let's think about another thing that I want you to already start thinking about, which is, let's suppose there is a treatment A and treatment B. Which one would you allocate more trials to or more impressions to as you think about it? Like, why should it matter? Why not 50-50? Very good. The distribution with a higher noise should get more weightage. So we could have named it after you, right? So you're just like a 50-year slave to this game. And the person who discovered this called it the Niemann rule, which is what is used. And the interesting part is it's a policy, and we were a little bummed up because it's a heuristic. People use it all the time. And Niemann used it in a very specific setting, but people use it all over the place. And the question is that this would be the first heuristic that comes to mind. Right? Everyone comfortable with that? So just keep in mind that there is something in the literature which people use for estimation, not exactly for this problem, but that's called the Niemann allocation. Okay? Good. So with that in mind, let's go with the randomized controlled trial. And in that setting, with the symmetric CI, what I've done is I've almost set up the policy for us. Now, if I follow that, we have the following condition, that whatever policy you follow, if you want to get a delta epsilon confidence interval from this, the amount of effort that you need to spend on it is given by this lower bound. Now, before we understand this lower bound, let's try to think about what the scale divergence is, which I've introduced here. I would simply say, just for the purpose of the analysis so that we get some intuition, it is essentially the good rate function in large deviation. That's what it is talking about, that if you have a distribution mu and it behaves like mu, what is the probability of it? And if you invert it to some degree, what you can get is, you can get the number of trials you need to do so that the error is bounded. That's where all of this is coming from. So what we have here is some expression, and I want us to look at it, understand where this is coming from, and then we will work on making this a general result for all the policies and how one will get. So it's nice to do this graphically rather than doing it in algebra. So the horizontal axis in this case is the mean of treatment A. As I mentioned, we are taking one distribution and converted all the exponentially twisted version of them. So what we have is the mean of the distribution then defines the distribution. It's a single parameter, that's why we call it the single parameter, because if you know mu n, you know exactly what the distribution is. Okay? Mu b, in a similar spirit, I draw that on the vertical axis. We look at that point where mu n, mu b is drawn. This could be considered as the space of the means, but I can also think about this as the space of all the distributions for treatment A and treatment B. So where they intersect, that's what the truth is. That's where everything is being generated from. Okay? Now if I take mu A and mu B, and I draw this 45-degree line and take it back to the horizontal axis, what do I have? The delta, the ATE, which we are after. Everyone good with that? Okay. Now, if you have a consistent estimator and at the stopping point, when you stop, you are going to give me an estimator. And remember, I'm thinking about delta going to 0 and thinking about the limit. You will have a limit which will be delta plus minus epsilon by 2. So notice the following. If I want to think about what should be the ultimate goal, you essentially want to rule out all the distributions which are outside this green zone. Right? If I can rule out everything outside my green zone, then that is the minimum time that you need, and we want to find it the efficient way to do that. That's how the lower bound will. Okay. Now, how do we do this? If you look at the expression is saying take all the x and y's which are outside the green zone. So now you can think about this particular minimization. And now comes the question, what is the 2 doing on the top? Now remember, if something in the numerator, if I want to bring in the denominator, it is the reciprocal of it. I know this is simple math, but my daughter right now is in 4th/5th grade, so this is a big deal in our house right now. Just saying. So if I take that 2, flip it over, it's half and half going to the mu A and mu B. Where is this coming from? This is exactly coming from the fact that we are doing randomized control trial and it needs to be 50-50. Everyone comfortable with this? Okay. Now, let's take a moment and think about it. If I want to run an experiment and I say it need not be 50-50, what do I need to change? Rather than half, I put in a parameter and I say, let's put W. So what will this be? This will be any allocation between treatment A and treatment B, but I've fixed that my construction needs to be symmetric around the consistent estimate. Everyone okay with that? Now let's throw the last thing in as well, the last chip. I say there is no restriction about it being symmetric. So now what will happen? Think about that, the green band that I drew. What am I allowed to do? Its width will stay the same, epsilon, the horizontal width of it, and I'm allowing it to also move. Great, guys. We have a lower bound, and that is exactly the general lower bound that we have. The first thing is, if I want to do a lower bound of a symmetric confidence interval, you allow the weights, and on top of it, if you want a general lower bound, you also allow the green width to vary. Perfect? It's not just a lower bound. It's even something more than that. What have you discovered? This lower bound also tells you, exactly, it tells you how you want to assign for your algorithm and how to construct. Why? Because at any point in time, the weights will be how you will assign for the future, and the delta L and delta R, which is the solution to this, will be the construction. That's great. So we are almost done, but we still have 10 minutes to spend. And that's where something more will happen. So I think where the state of the knowledge right now is, at least based on our understanding, this is something, a part of which is proving these are great, but following this, like we want to understand what more is happening, because this is still like a black box. We did a lot of things, but we're not able to tell it to someone, okay, why or how it's working. We have some idea, but the question is what exactly is going on. So we want to draw a little bit more insight, but we have the policy, we have the lower bound, and we'll talk about exactly that. Oh, this is coming from there is a function that we are trying to, when we do this formal proof, because it's an exponential term, that's where it is coming from. The 2.4, there are a couple of constants that people use. The 2.4 is a little bit more precise, but because you're doing essentially, there is a information theoretic bound where it's coming from. Vikas, is that the right way to say? It doesn't matter, the 2.4. The 2.4 is just like, I'm just showing off that I know that constant. That's okay. Okay. So, as was mentioned, there is just, now let's just write down formally what the policy is. The policy is allocation rule-wise, take your estimate for mu A and mu B so far, plug it into that optimization problem, There is a small caveat, and that's why I've written it in smaller font. You have to make sure that you at least get root n customers just so that you're picking up the things correctly. You construct delta L and delta R exactly from the first order condition, which is from the optimization. Stopping time would be, we need to make sure that you have collected sufficient, and that's where a lot of effort will be spent to make sure that it is delta correct. We can actually have the following statement. This is asymptotically optimal policy. The biggest problem that we have with such a policy is in implementation that you need to solve that optimization problem. It might have good structure, but it might not have such a nice structure, and that's what the problem is. Everyone okay? Now, whenever you hit a roadblock like this, my recommendation would be to try for distributions where you know the functional form. And the KL divergence is very well known for the normal distribution. In fact, if I think about the confidence interval tutorial, they were all around, it started from the normal distribution. It was, the whole idea was because the moment function is so nice to write, because they become like quadratic. Okay. So what I'll try to do is this, let's start there and see what we get. Okay. So we want to understand this. So let's start with the Gaussian distribution. For the Gaussian distribution, interestingly enough, the setup that I have forces me to have distributions which will have identical standard deviation. So the noise is already fixed because there is only a single parameter which can vary, and that is the mean. And my answer comes out to be W star is equal to half, but this is what the RCT policy is, right? So, okay, so much effort and nothing come out of it. That's not true. Remember, this is only when the Gaussian have the same noise. If I do a more general version, when the variance is not the same, we can still solve it because remember the whole machinery still works. It's a little bit outside the, like what we theorems, but it is still applicable. And what we find there is that your weight is essentially coming from this Fisher information, which essentially is saying that it is inverse of the standard deviation, right? So the more noise you will have, we will sample it more. That's what you will do. And the less noise you will have. But this is something that we already had some intuition for, right? So, sorry. So the Neiman allocation, which we discussed, that turns out to be optimal. That's true, but not entirely. So that's where we will say a few words more. So that's absolutely true. And this basically suggests what now? This is suggesting that the Neiman allocation is optimal. But notice the following. First of all, just to be clear, this is just for Gaussian so far, right? Now, the tricky part is, look at the problem statement. There is an epsilon in it, right? And that causes it not to be this clean. So with Gaussian, what happens is that epsilon falls out and the optimum does not depend on epsilon. So the key thing that I want you to take away is not the fact that it is RCT or Neiman, but rather epsilon is falling out of the optimization problem, which means that you do not have to worry about what is the delta epsilon width that you're allowed. Okay? And the first thing we did is we said, okay, to understand it, let's take the general distribution. And we did a bunch of those, and this is what the plot looked like. On the horizontal axis is the width that you're allowing, and the different graphs are different distributions with different means. And what do you observe in terms of the curves? For the Gaussian, they were straight lines. With exponential and Bernoulli, while they're not the straight lines, they're not changing that much, right? So there is some sort of insensitivity. And this is what led to the following thing. I'm going to put it here. We can actually prove it theoretically that if you were to do a Taylor series expansion of the weight in epsilon, you will find the first term will be 0. Fair enough? And not only that, if you're a little bit more patient, you can actually identify the second order term as well. Okay? Now, why will this be useful? This will be useful in writing a formal result. Keep your eyes very close to the slide in terms of making sure, because I'm going to play a game of what changed. So this is policy P1. We are following this, and this is the first one that we came up with. And we said this is very expensive. Why was it expensive? Step one was expensive because you're solving it again and again, and with epsilon it gets more messy. Okay. Now we can do the following. We can take this epsilon and remove it, and prove the asymptotic optimality as delta goes to 0 and epsilon goes to 0. So it's for small epsilon. And we can write down a formal result which shows that this will be the best thing. What is the difference? I'm not talking about W star now, which changes with epsilon with W bar. And W bar, I know it is simply the Fisher information. So that's all awesome. But what has happened? Fisher information for some sort of, these class of distributions were all turning out to be the standard deviation. And that's where it leaves us with the rub that it's all still Niemann. It's nothing more than Niemann. Okay? So in interest of time, what I want to now show is that that's not the only thing. Which is, here is the question, which is Niemann always asymptotically optimal? And the answer is no. This is only true if there is single parameter exponential family with the canonical one. What is the canonical one? Canonical one is where the sufficient statistics is linear. This does not cover the heavy tails, for instance, like Pareto will not fall into it. And the question is, will there be something more happening there? And let me now show you what we observe. We can still construct our policy. We can still define Fisher information, but Fisher information will not be the standard deviation now. So what happens in this particular case, if I run it for the Pareto distribution, let's compare the three policies at hand. One is RCT. The first, means I'm starting from the right rather than the left, RCT, P2, and P Niemann. And what do we observe? While Niemann was supposed to be optimal in many cases, if you use it blindly, it will be even worse than RCT. Right? So that is where there is value of knowing the distribution family. But if you don't know the distribution family, you might want to use P2 over Niemann, because when Niemann will be optimal, it will coincide with Niemann, but Niemann is not always optimal. And that's the conclusion. Everyone okay? So with that, I want to now compare with the BTI, which is how will your policy look like when you're doing the best treatment identification versus the average treatment effect estimation. Do they look the same? Do they look different? So notice the following. Let's imagine that mu A and mu B both are 10. So it's a symmetric case. Sometimes people refer to this as AA test, which is how do you test the efficacy? There is no effect, and the question is, are you really picking up something or not? And in this particular case, you can clearly see that the optimal thing will be what? You want to do 50-50 because any kind of deviation, there is nothing underlying difference, so you would want to spend equal effort. Both BTI and ATE will be at that particular point that you do 50-50 allocation. Okay? Now, interestingly enough, as we go away from it, I can draw the curve of what ATE comparison would do and what the BTI would recommend, the optimal. BTI is known from literature, ATE is what we developed, and this is how the graph looks. And the key thing to notice is it's not just they're different, their behavior is also different. And in the paper, we actually prove it, that this behavior is actually dependent on, remember the W bar that I have, you can actually do a Taylor series expansion to talk about how it changes with the mean, at least in the neighborhood. And what we can show is that the behavior actually behaves differently. And this has to do with the sign of these two things. And these signs are always opposite because we want to reconcile. I can be very clear about it. They always go the opposite. But now comes the question with Gaussian. We know they are same. So Gaussian creates an impression that like they are the same. And the answer there is not entirely true because Gaussian, this term is 0. That's why it's matching up. But in all other cases, they actually go the opposite direction. Okay. So with that, I'll just conclude the talk. What are the things that we have done? We first things first, we developed an asymptotic lower bound on the expected sample size, looking at the question about average treatment effect estimation to deliver an epsilon delta confidence interval. Step 2, we developed an asymptotically optimal adaptive policy, but computationally it was very expensive because it was resolving that optimization problem at every step of the way. And what we do is we constructed or showed that asymptotically optimal, the asymptotically, if you send epsilon to 0, that particular treatment that you need actually depends on the square root of information. And if you do that, you will do as well in practical settings. And there is a theoretical result, which is double limit delta going to 0 and epsilon delta. Okay. Lastly, the optimal allocation for ATE is quite different from the optimal allocation for BTI. And the comparison between Niemann and RCT and our proposed algorithm. And the key thing there is that, yes, Niemann is optimal, but not always. Right? So that's all that I have. Thank you so much, guys.
So very short, this BTI and ATE are the same for Gaussian. I also noticed it is same for mean 0.5 Bernoulli. Can we extend it to distributions which are kind of symmetric?
That's a good question. So I think what happens is in both of these cases, like 0.5, they are the same. But if the two distributions are the same, they will be the same. So it's not the symmetricity which is there. It is the fact that the distributions are the same.
The distribution itself is like is a symmetric distribution modulo some translation.
I don't think it's just a symmetricity, right? If I'm not mistaken. Exactly. That's one. The other way I would argue to think about this is like if you think about the KL divergence, those curves matter and they're quadratic and that's symmetric. For Bernoulli at 0.5, if you draw, they would look the same, but once you go left and right, like locally they look looks very symmetric. But once you start going on either side, it comes out. So locally it looks the same because all of these are Taylor series. So at least my understanding is the local behavior, if it's very, very symmetric, that's what you pick up. But if anything else is happening, then they're not.
What's the intuition? Why is there a difference between ATE and BTI allocation rules? Is there an intuitive?
So ATE is going after, if I think about it, and let me be honest about this. This is a half-baked intuition, right? So ATE, if I think about it, it is definitely clear that it is the Niemann kind of the allocation, which is you're trying to control the noise because you want to know the width, and the width can only be addressed if the noise is diminished, and that's what we are doing. In contrast, if you want to figure out the better arm, right, then you're not so much concerned about knowing exactly where this is. Rather, you want to construct a band, and as long as the band goes one way, you're done. So, Shubhita, I can actually give you an example because someone mentioned this, and that was a great way of thinking about it. Notice the following: if you want to figure out ATE, and your estimation has bias and variance, you will try to minimize both of them. Why? Because you're looking at the difference. So bias and variance both hurts you, want to remove all of that. But if I want you to figure out which is the better arm, then as long as you can control the bias, you don't care about eliminating, right? So someone mentioned this in a different context, but that actually applies here. It's not a bias in this particular story, but you can clearly see that these two problems are different. Because what you want to know is you really care about that this is above the other, whereas ATE really wants to bound where it is. The second thing is if we sit down and look at the KL divergence plots, that gives a very more interesting story because it tells you exactly what the first order condition is. And there you can get an idea about the way they are shaped. Interestingly enough, just the opposite thing matter. And that's what like the beautiful table that Vikas has. it actually shows the sign of those things because you meticulously put them there to show that in all those cases it happens to be occurring.
So I wanted to ask if you have deployed it in the test setting because while I was at ABP News, we launched this chat bot and we tried to do A/B testing on it. But it's very difficult to find a truly homogeneous population for treatment and effect group. And there were like we had an effect size of certain percentage, but it was like very arbitrary.
So,
So
so we have not deployed it, but I can tell you at least based on our conversation with Netflix and other places and how what at least what we have read about how A/B testing are deployed. The idea there is that you want to apply them as people are coming in. You're splitting them into two streams because you do not want there to be any other assignable course. Just to give you an example, you cannot do that. I will assign everyone who's coming at 8 o'clock A and everyone who's coming at 10 o'clock B. Right? What is the reason behind that? Because now the behavior of the people who come at like 8 a.m. and 10 a.m. will be different. So the beauty of A/B testing is that it is applicable exactly thinking that if the people are coming in, I'm flipping a coin to determine whether I give them A or B. Hopefully the people who are coming is a homogeneous stream. Means homogeneous means they don't have to be identical, but all the behavior that they have in the two buckets looks the same once I just flip A/B coin to allocate them one versus the other.
Hello. Yeah, so I just wanted to ask for like example drugs or vaccination. I just wanted to ask that are the people whom we are doing this A/B testing, are they aware? Because for example, if they are aware of the drug and then if they know this information that like, this is how it is done, maybe I will be thinking in myself like, oh, have I actually been given the actual drug or like I'm like, nope, that might, yeah.
Absolutely. So in medicine, when they use A/B testing, they do not review. So first of all, so let's talk about a couple of things there, right? Why will people be willing to allow people to test them on themselves, right? First of all, that's the first question that we should ask. So if the medication is something where there is no drug available, people want to get on to these medications, and the doctors themselves would recommend that you will be a great candidate because there is means we have get unfortunately we're at the end of the rope with you, but if you go in, there is a chance that you will have it. So many people that I know who have done this, like if it's a disease of at that level, that's what happens. If it is more of like I'm doing like a cough medicine and other things, then they initially make sure that the toxicity level is low. And so there is an efficacy stage and toxicity. These are the two things that people look at to make sure that the drug will not harm if it's not helping. That's one. The second thing is people who are given placebo or the people who are given treatment are not told what they are given. As you can imagine, means all of us have this, like psychologically we feel better. Means sometimes by just going to the doctor, you start feeling better, right? He hasn't even given any medication, but you start feeling better. So to make sure that we capture that effect, means just to be clear, means I have seen like in my family, for instance, like especially someone who is old, you just tell them that this is the medicine and you'll feel better, and it's just simple placebo, right? You give them vitamin capsules. So this is exactly it works because it actually gives them, but you measure like is there a real effect or not? But people are not told during the experiment. So in this particular case, it will exactly come out that the RCT will be optimal or near optimal. There will be, because of epsilon, there will be a slight variation because the curve would look slightly different. At least to the best of my understanding, the allocation will be close to 50 because the variants are different. Yes. So that is the part that I completely pushed under the rug. So the way that works is this, if you remember, what you will do is you will look, broadly speaking, you'll have a likelihood ratio, if I want to think about it. And the idea there is that that particular term, the log likelihood ratio should behave in a certain manner. And if it goes beyond a particular threshold, that's where I will stop, right? And that is exactly what it is prompting us to know that we have enough confidence in what we have studied for. So just in terms of like how we want to think about it, there are two algorithms that comes out of it. One algorithm does the following. At every moment in time, you will construct an interval which will be delta correct, but the width will be much wider than epsilon. So what you will do is at every moment in time, you're constructing a confidence interval, which is what we call as delta correct confidence interval. So the probability you will lie in it is delta correct, but it is too wide. In this particular case, it's easy to think about what is going to happen. Over time, you will keep on making sure it's shrinking. And when that width becomes less than epsilon, I will stop. There is a similar second one, which is a little bit more nuanced, because what you now do is every moment in time, the width is epsilon, but your confidence is not at delta. So when that confidence gets delta, then you stop. We personally prefer the first one because it also have other properties that I did not discuss, which is what are called confidence sequences, which is an interesting set.